Hello, welcome again. We are going to continue our discussion with tree data structure. So here the idea is that tree has the recursive structure, okay, and the height of a node in the tree is one more than the maximum of the heights of its immediate child node. So here, what it means that height of a node, say let's consider the root node, okay, and we saw that the root node has the height 1, 2, 3, 4, okay. So now how we can find the height of a root node? We can find the height of a root node by using the height of its immediate child node. We know the properties of recursive algorithm, right? So for the recursive algorithm you can actually consider a sub problem, and you can use the solution of the sub problem to find the bigger solution, okay. So for the sub problem, for example, say the root node has three immediate children, 2, 3 and 4. So the height of 2 is 1, 2, the height of 3 is 1, 2, 3, and the height of 4 is 1, okay. So here we can consider like the max of these three height, okay. Root height of 2, okay, so let me write that. So max of height of 2, node 2, so height of node 3 and height of node 4, okay. So this max value plus 1, so the height of a node is in the tree is one more than the maximum of the height of its immediate child node. So for the root node it has three immediate child, 2, 3 and 4. Now if I know the height of these 2, 3 and 4, I can use them to calculate the height of root node, okay. So that is one property of recursive structure. So and that's how I can use the solution of the sub problem to calculate the solution of the main problem, okay. So here height of 2 is 2, this one has 3 and this one has 1, okay. So the max value is 3, so the root node has the height 3 plus 1, okay, so which is 4. So now let's think about how we can represent a tree, okay. All right, now another form of tree is known as binary tree. So in this discussion we talk about tree like as a general tree. So general tree means each tree will start from the root node, and each of the node can have uh, each of the node can have one or more children, okay. Some of the node may not have any children, which are leaf node. Now one form of tree is known as binary tree. Binary tree means each of the node can have at most two node, okay. So each of the node can have at most two node. So for example 0 has two node, now 1 has one node, 3 has also one node, so these are the leaf node. Node 6, 9, 8, 5, these are the leaf node, but each of the node can have at most two nodes. So if a tree if this is the property for a tree, each node can have at most two nodes, this tree is known as binary tree, okay. So we are going to see an example how we can represent a binary tree. All right, so here I mean the data structure is completely different from other data structure that we have discussed so far, right. So here we have the hierarchical structure, that means we need couple of information. All right, so that means we need all the information that who is the root node, who are the children node, and each of the children node can have also other child node, okay. So one format is that one format is that we can represent the information of the binary, we can represent the information of the binary tree or a tree as form of a file. Okay, so this is an example of a file where we can store the information. Say for example, say here node 0, the root node will always have the id 0. Okay, so node 0 is the first node, so this is the root node. So node 0 have two children, 1 2. So one node, they are the id of the node, so we are going to represent each of the node with a unique id. So node 1 has 3 and -1. So -1 means it doesn't have the right children. So as binary tree has two children, so we can say that one is the, this is the right child, so this is the right child and this is the left child. Okay, so 0 has 1 and 2, two child. 1 has only left child but no right child, so we can represent them with -1. -1 means no child. So node 2 has 4 and 5, one left child, one right child. Okay, so 3 has no left child, only right child, so 6. So 4 has 7 and 8, 4 has 7 and 8, and 7 has one left child, no right child. Okay, so if the left and right child is not there, we are going to represent them with the id -1. Okay, so so for binary tree to represent a binary tree, we need each of the node. Now each of the node means each of the node is going to have one id, and each of the node is going to have two children. So one is the left child and another is the right child, and we have to explicitly identify that which one is the left child and which one is the right child. Okay, so we show a node and its child nodes in the file only if the node has at least one child node. Okay, that means for the leaf node you can see that they are not available here. So node 6 there is no any information, on node 9 there is no information. So this is just a sample of sample representation means a sample file where we can represent the information of a binary tree. So this is a sample code how we can, if the file is looks like this is a normal text file, but the format is going to look like that. Okay, the parent node, then colon, and the first is the id of the left child and second is the id of the right child. Okay, so if there is no child as a left or right child, we are going to represent the id with -1. Okay, so if the file format looks like this is a sample code how we can read a file with this specific format. Okay, so this is actually, I mean, the idea is that we are going to just read every line by line. Okay, I mean, we know already how to read from the file, but it has a specific format. This is just a sample code how we can read this information from that file. Okay, so we are going to read line by line, and we are going to assume that each line is going to have maximum 10 character. Okay, so we know each line is going to have this following information: the root id, okay, so sorry, the parent id and the child id. So left child id and right child id. Now based on the id number of each of the root, each of the node, we are assuming that each of the line can have at most 10 character. Okay, all right, then we're going to read each line by line using getLine function. Then what we can do, we can just tokenize each of the we can just declare a string tokenizer, and we can declare a character pointer to the token extracted. Okay, and these each of the token we are using the delimiter as a comma and colon. Okay, as we see in our file format. Okay, so that's how we are going to find each of the token. All right, so each of the token means is the ID of the node. All right, so each of the different token is going to be the node ID. All right. Okay, now that was the information if all of the information of the binary tree is written in the file. Okay, so we have to have a program how to open the file and how to read the node ID information. Now when we have the information, now actually the job is to define a data structure, how we can represent the binary tree. So obviously this is going to be very different from the linear structure. Okay, so here just let's look at this structure, and first of all we have to have the data structure to represent each of the node. Okay, then we are going to connect each of the node with their parent and their children. Okay, now if we look at the node, we said that each of the node is going to have a node ID, and each of the node is going to be connected with a left children and each with a left child and with a right child. Okay, all right, so the data structure of this is also is going to be, if we are going to write a class, let's say binary tree node. So the member variable are going to be, first of all we are going to need a ID. Okay, ID, and each of the node also can have a value. Okay, so data or value. All right, so then each node is connected, each node can be connected with at most 2 nodes. Okay, so we are going to need a pointer. One node can be connected with another node of the same data type. So we are going to need a pointer that can point to the same type, bt node. So for the tree we represent them as a left child, say pointer, and bt node of the same type of right child pointer. Okay, and another optional variable we can consider them as a level number. Okay, so these can actually help us to traverse the to traverse the tree. So this is optional, but one optional member variable we can store as a level number. So for each node, we saw that for each node is each node is in a specific level. Level is actually same as like the depth. Okay, so we can also consider them as a private as a member variable of the data structure. Okay, to represent each of the node. Okay, so each of the node, we can see that here each of the node has an ID, the value associated with this node, level number, and the pointer that can point to the same type of left children point, and another is going to point to the right child point. Okay, so right child pointer and the left child pointer. So the left child pointer has the address of the left node, and the right child pointer is going to have the address of the right node. Okay, so if a node doesn't have a left child or the right child, they are going to be set to null. Okay, so for example this node has only one right child, so this will be set to the, this pointer will be set to the null. Okay, and for each leaf node leaf node doesn't have any left child or right child, so they will be pointed to the null. Okay. Now one strategy to create a binary tree. So this is the data structure, this is the class definition of each of the node. Okay. Now a binary tree will be constructed by connecting one node to another node hierarchically, each in each level. Okay. So each node has to be now connected with its child node. Okay. Now one strategy to create a binary tree, what we can do, we can create a array of binary node. Okay. So let me show you directly, let me show you the example. So what we can do, one strategy is that depending on the total number of node, and now as we are reading the information from the file, so after we read the information from the file, we will know how many node this tree has. Okay. All right. Now depending on the number of node, we can declare a array of node. Okay. Array of binary node, I'm sorry, array of binary tree node. All right. So initially we are going to read the file and set up the pointer to the child node. Okay. So we are going to read from the file. From the file we are seeing that it has total 9 node. Okay. So we are going to create a array of binary tree node, and this array has total 9 node. So each of the node, initially each of the node has the left pointer, left child pointer and right child pointer. So initially they are going to point to the null value. So this symbol is indicating null value. Okay. All right. So okay. So these are just, we are first collecting all the nodes. Now we are going to construct the tree. So by constructing tree means now established all the relationship from the parent to child. Okay. So this is our step 1. Okay. Now after step 2 we are going to construct the tree. So the constructing the tree means we are going to now point, for each node we are going to point the left child to the address of the left child and right child to the address of the right child. Okay. So after the step 2, our array is going to look like this. Okay. So node 0 has children 1 and 2. Okay. Node 1 and node 2. So for node 0, this is our node 0. Node 0, the left child is going to point the address of the node 1. Okay. So 0 to 1 and 0 to 2. So 0, it has the right child. The right child is going to point to the node 2. Okay. All right. Okay. So node 1 has 3, that means it has one left child and no right child. So left 1, node 1 is going to point. So here this is going to store the address of the node 3, and the right child is still pointing to the null. Okay, because it doesn't have any right child. So after step 2 we are going to store all the information of the left child and right child. So each of the left child and each of the right child is now going to store the information of their left child, that means the associated node information. Okay. All right. Now this is the tree and this is the representation. This is the data structure representation of our array based representation of this tree. Okay. So node 0, 0 to 1 and 0 to 2. So node 1 to 3 and 3 and right child is null. Node 2, 2 to 4 and 2 to 5. 2 to 4 and 2 to 5. So this is the class definition of our binary tree node. Okay, so each of the binary tree node has these 5 member variables, and we know based on that we are going to write the constructor, accessor function and mutator function. Okay,